Okay, so today, coming back to our multiple server queue model, basically to prepare for another modification of that. Okay, so what we've seen so far is starting with our most basic model where we're simply counting number in the queue and the number of available servers, and then at some point when we wanted to collect more information about our customers, we transitioned to modeling them explicitly as entities so that each entity represented a customer. And one of the advantages of doing that were that we could then get more information out of that than we could at least directly from our just counting model. And in itself, thanks to Little's formula, there's not necessarily a whole lot to be gained from that, but that leads to this reneging model that we had, where it is pretty much crucial to capture or model the individual customers as individual items, or entities in this case. And the reason for that is because simply counting, say, the number of reneges and the other ones, does not get, Little's formula actually doesn't help us there because we now have two different things. So in that model, if we wanted to get things like the delays in the queue and the times in the system, et cetera, then pretty much the only way to do that is through something like the entities. We saw that there was a way of just doing the count-like thing by just giving each one an integer, but integers don't have a lot of information. As you saw with the last computer assignment, if we now model the customers as entities and give it more information, then we can do things like compute the delay in the queue for those who renege versus the delay in queue for those who actually got service. So now we're going to apply the same thing to our servers. So one of the implicit assumptions about our model is that the servers are homogeneous. That is, each server has more or less the same service time. That's what is it that distinguishes one server from another? In the model, the main thing is the service time. And in the models where we had, say, two different types of servers, what distinguished one server from the other was we had the fast ones and the slow ones, and so they each had their different service times. But within those, they were still homogeneous. So if we had 5 servers of type 0, they all had the same sequence or the same probability distribution, if you will, for service times. And same for the type 1 servers. But what if we're in a situation where each server is actually a little bit different? I mean, that's a little bit more closer to the way the situation is. So if we have various workers, for example, they each have a different level of skill, a different level of training, and that's going to affect how the speed with which they can process their tasks. Even in machines, after, maybe out of the box, machines are going to be exactly the same. But after a while, each machine kind of can start to develop its own personality, if you will. So even if I have 2 identical machines at the beginning, after a while they may operate a little bit differently. Our models so far have not been able to capture that. Why? Because of this implicit assumption of uniformity, that is, or homogeneity. That is, every server of a particular type is the same as every other server of another type. So how can we start to examine that assumption or deal with a situation where the servers are going to be a little bit different from each other. Okay, so none of our models so far can handle that. So taking our inspiration from the fact that when we went from simply counting customers to modeling them as individual entities, why not just model the servers as entities? And why not indeed? So let's look at a model where, again, we're back to our multiple server queue. And now we're going to use entities for both the customers and the servers. So hopefully we've seen the advantage of using the entities for customers. So even in our basic multiple server queue model, that allowed us to explicitly estimate delays in queue and times in system without having to wave our hands. So Little's formula. Depending on who if you were briefing this to someone and depending on who you're briefing it to, if you're briefing it to a simulation modeler or a statistician and you invoke Little's formula, nobody would blink an eye. If you're briefing this to someone who doesn't know what that is and you try to explain Little's formula, then you may get kicked out of the room. So on the other hand, you say, okay, we're modeling our customers and each one comes through and they say this is how long they were in that, then you don't have to be a simulator to understand what that is. So again, if we want to represent our servers as entities, then there's a similar advantage. So what does that look like? Now we've already seen, I think that there actually is a significant advantage to taking our processing times for our customers and putting them into the customer entity. So given that we have customer entities, so a basic customer entity looks like this, where you basically carry along its processing time. In the reneging model, it was also called a customer there, and it carried along the processing time as well as the renege time. So in our basic model, we don't necessarily have a renege time. We could. It wouldn't really necessarily matter. But again, so we have our basic entity, which carries along things like our timestamp and creation time and all the other things which have hopefully proved valuable in being able to invoke just to get the information that we want. So, and then just to start with, we'll just have plain old entities representing the server. So our model looks like this. So again, now in terms of our parameters, we now have to look a little bit more carefully here. So we have, say, the total number of servers, but really, if we're modeling the servers as entities, then we want a parameter, which I'll call all or all because that's a little shorter than all servers. So basically, if we have an array of entities that are going to be our servers. So by analogy to, and actually I think in this model we're actually not going to use K, but that's, okay, so our state variables now, we have our delays in queue and time in system, because those are the things that we're kind of after. But now we have a container of customer entities that are waiting for service, that's our queue, and then another container which will consist of all of our available servers. And initially it's going to contain all of the server entities that we have. So in a way, this is kind of why you may have been wondering why from the beginning we have been modeling the state variable as the number of available servers in a way that's motivated by a situation here where if we are representing our servers explicitly as entities, then in the beginning we have a container that has all of them, and there are going to be K of those. Okay, so let's see how this event graph component would look. So in terms of our Q and D and W, that is the container for the customers waiting for service, and for our tally state variables, or our transient state variables, as it were, that's all kind of the same. But to initialize our container of machines, we want to put all of them in into the container at once, or in the beginning. So, and you could just sort of say something like add all, although again in Java you actually can't do that. You'd have to do a little bit of a dance. You'd have to turn the array of entities into you could turn it into a list, and then just sort of pop that list in. So that could all be done in one fell swoop. But if all we have are the language of event graphs, then we can use this for loop kind of concept. In other words, for each of the entities that are servers, we will schedule an init and simply add the ith element of that array. And so when this is done, then then we have all of the servers are in this container of servers. Okay, so looking at the state transitions, so we have our arrival event, and we're going to do the same as we've done before. We're going to stamp the time of this arriving customer and add it to the queue. Fairly straightforward. Okay, so now our start service event, again, what is it that causes a state transition? Well, what causes a state transition for our queue is to begin service. So we're going to pop the top guy off. But now we also need to pop off a server entity. So instead of S being S minus 1, we pop it off here. And so now this little s is an entity. And so you have to be careful. Like in the past, sometimes when I've asked you to, not you, but the previous yous, to formulate something like this, every now and then there'll be, like if you have like a container, I see something like this, Okay, so that's obviously not going to work because this little m, that's a container. And I can't subtract one from a container. I have to, if I want to take something off, now here I'm popping, and again, if we're using sorted sets as we are in the Java, then we have to go do this little dance of getting the first one and removing that one. Okay, but again, conceptually, it's the same situation as I was describing before. This event, like when we're removing something from a container, it has the moral equivalency of subtracting one from an integer state variable. In other words, these two state transitions, popping a customer off the queue and popping a server off the available servers, that will only work if both of these containers are not empty. If one of these containers are empty, then you're going to get an error. In a program, you'd get this runtime error and the whole thing would bomb. In the event graph, we don't have that ability because we're not actually running it. So in this, you have to be the discrete event engine in the sense of looking at this and saying, how is these state transitions protected by the preconditions of the events? So here, the queue precondition is protected by the fact that when we're scheduling from the arrival event, we have added somebody to the queue. And so when we schedule the start service immediately, then we will be able to pop off, at the very least, this one guy that we've added. So this piece is protected by this state transition. But what about the popping off an entity from the available machines? That's protected by, by this mistake, which should be M. I will correct that when. Okay, so it's protected by the fact that the container M, the condition is that the container M is not empty. So when start service occurs, and again, that's part of why we schedule it with a high priority, meaning that that's gonna go right to the top of the event list and be the very next thing to happen. Similarly, when we have an end service event that adds an entity, a server, back into the container of available entities, that will guarantee the precondition for popping off another entity. But what about the queue? That's protected by this condition that says queue is not empty. Now, the final thing to look at for this model is notice that because the end service event has both a customer and a machine. We need the customer to find out how long they've been in the system, and their elapsed time is going to be the time between when this customer showed up at this event and when they had stamped their time on arrival. But now we need to add that machine or that server back into the container of available servers. And so if we did not pass the server, we would not be able to perform this state transition because we wouldn't know what S is. So you need to tell it. And likewise, we need to know what customer just finished service in order to compute the time in the system for that customer. So the other thing about this is notice that now we have an event that has two arguments. So far we've seen events with no arguments for a while. We've seen events like init and some other ones that have one argument, or arrival here that has one single argument. And here we have an event that has two arguments. There is no limit to how many arguments an event can have. The one constraint, though, is that when I schedule an event that has two arguments, I must pass two arguments. And those two arguments have to be consistent. They have to match in type forms. Now, event graphs by themselves don't enforce type stuff. I mean, in programming, your IDE is going to enforce type matching, but here we're just dealing with pencil and paper. So in other words, the end service event needs a machine and a customer. And this is going to be just a plain old entity, and this is going to be a customer instance. So the lesson, though, is, and then notice that start service doesn't have any arguments. So there's no, it's not that the lesson you should take from this is that how many arguments should an event have? It should have as many arguments as it needs in order to perform its state transitions and its scheduling. In other words, it just needs as much information as it needs in order to do its job. And what does an event have access to? Three things and three things only. It has access to state variables, it has access to parameters, and it has access to any arguments that get passed to it. Those are the only three things.
What's the H in the circle representing?
What is the what?
The H in the circle?
The 8. Oh, the H, I'm sorry, yeah, that's the priority. And that,
What's the point of the priority edge if all the incoming edges to that state transition are high priority? Doesn't that just kind of cancel each other out?
no, because each of these events are going to basically happen one at a time. Remember, that's how the event list processes things.
Mm-hmm.
So,
I'm saying with the start service event, both the incoming edges are high priority. What do those high priority labels mean in context?
it means that if there's any other event that happens to be scheduled at exactly the same time, then events with higher priority will be executed first. If I have two events that are scheduled at exactly the same time, then it is arbitrary which event happens to get executed first.
So you could just remove the high priority labels going into the start service event there and have the same result. But if one of them was high priority and one of them wasn't, you'd have a different result eventually.
Yeah, and that comes up only in certain contexts. If in practice most of the times are continuous random variables, and in that case the probability of any of that happening is essentially zero. For some reason, some people get fixated on kind of time steppy types of things, and so they'll use discrete random variables to have their, say, inter-arrival times and service times. And in those conditions, it is more likely to have situations where, say, I have an end service event at exactly the same time as a customer arrives. And then in that situation, it doesn't matter which one happens first, but if what that guarantees is that this state transition will only be executed under the right circumstances. So because start service would have high priority in those cases, and I happen to have an arrival event and an end service event at exactly the same time, then the start service event would occur first, and whichever one of these happened to get scheduled first would schedule the start service event. And because that's high priority, that would happen before, let's say, the arrival event, which is technically at the same time. But then, because the start service event now has performed its state transition, the arrival event may find the servers empty. Whereas if the arrival is allowed to happen first, then, and I happen to have an end service event and an arrival event at exactly the same time, then I could have two start service events scheduled where the second one would drive the states into an inadmissible condition. Okay, so that will be